Hello, Math 200 statistics students. We're on 2.2. 2.2 is more and more of what we did in 2.1. It's just more graphs and displays of statistical data. All right, the first thing we talk about here is a stem and leaf plot. It's the example of an exploratory data analysis. It was developed by this guy, I'm not sure if I know how to say his name, John Tukey, in 1977. All right, separated into stems and leaves. So we take the data. All right, this data lists the number of text messages sent last week by the cell phone users on one floor of a college dorm. Display this data in a stem and leaf plot and describe any patterns. All right, so because the data go all the way from 78 to 159, we're going to use 2 digits. We're going to use the tens digits, as our stems, and the ones digit as our leaves. So our stems are going to start with 7, and they're going to go all the way to 15. But why do they go from 7 to 15? Because our lowest number in this is 78. So the 7, that's where the 7 comes from. Our highest number here is 159. That's where the 15 comes from. And then we just cover every integer in between there. Then every time you have a data entry like 155, that means we're going to put a 5 beside the 15 because the 15 comes from the first 2 numbers, the 5 comes from the last number. So there's the stem is 15, the leaf is 5. Next is 159. So that again goes on the same stem. It comes right here as the leaf on this 15 stem. For 144, the 14 is going to be the stem. The 4 is going to be the leaf, so I put the 4, you write the 4 right here, as the leaf on that stem. All right, notice that all of these are written in order, so the 4 didn't come first because there was a 140 and a 142. There's a 0 and a 2 before that 4, and there's two 145, so there's a 5 and another 5 after the 4, as well as a 7 and an 8, and so on and so forth. So here is your stem and leaf. This kind of does a good job of showing you the data because, like a histogram, it shows you the data broken up into different classes. Like this whole class goes from 70 to 79. This class goes from 80 to 89, 90 to 99, 100 to 109, and so on. But it's not just a bar. Although it kind of looks like a bar, it's just the numbers are kind of making that length of the bar. But you not only get to see a bar, you get to see the exact numbers of those data entry points that are in there. So it gives you more information. Notice it gives a key. It says the key 15 with a bar, with a line, and then a 5 means 155. So you always include a key with your stem and leaf plot. All right, there are variations of the stem and leaf plot. This is the same data, but grouped a little differently. Notice they have 2 7s. That means the first 7 actually goes from 70 to 74. The next 7 goes from 75 to 79. 2 8s, 2 9s, so on and so forth. And so it splits all those groups up into 2 groups. So the 12 and the 12, that's 120 to 124. Then the next 12 is 125 to 129. You can see how that spreads the data out a little bit more. Okay, another way to describe the data with a graph is with something called a dot plot. All right, a dot plot. A dot plot plots a number line. All right, you got a number line here. And the number line goes all the way from 75 all the way to 160. So it basically covers the entire span of all the data because our lowest number was 78. Our highest number was 159. So it's going to cover all the data. And every integer has a dash. And then every time you have a number, like 155 is our first number here, we're going to put a dot above the 155. 159, we're going to put a dot above the 159. All right, for 126, we have multiple entries at 126, and so we put a dot on top of a dot for every time we have a 126. So it looks like we have 5 different entries at 126. All right, so a dot plot also gives you a lot of information. It gives you the, you can kind of tell the frequencies as they're grouped, but you can also tell a little bit more than just the frequency distribution, because it's giving you the exact numbers. Like we have 5 dots representing 5 cell phone users that sent 126 text messages. Okay, next, graphing qualitative data sets. We can use something called a pie chart. A pie chart is a circle that is divided into sectors that represent categories. So let's look at this example. All right, here is the data. We have types of degrees: associates, bachelor's, master's, and doctoral. And here are frequencies for those different degrees. There's 942 associate's degrees in the sample. There's 1,716 bachelor's degrees in the sample, and so on. And then it gives the relative frequency. How do you get this relative frequency right here? Okay. You say, well, this is 942 out of what? Well, you have to add all these frequencies up to know how many there are. So if you add all those up, whatever total you get, you say 942 divided by that total. And that gives you the percent, or the decimal here, which is 0.265 or 26.5%. All right, so 26.5%. The next one is about 48%. The next one's about 21%. And the last one is about 5%. So then you just do the best you can to construct this pie graph with each of these categories getting that percent of the pie. So like for associates, 26.5% is a little more than a fourth. So I'm going to draw this section of pie that's a little more than a whole quarter or fourth of the pie. The bachelor's degree is going to be a little less than half the pie, right? It's going to be 48.3. That's almost 50%. So notice this section covers almost half, not quite. And then the 20.6% for the master's is about a fifth of the pie. And finally, this 5%er, that doctoral, is the sliver that's left there. That's called a what? A pie chart. Next, we have a Pareto chart. A Pareto chart is another bar graph. It's a vertical bar graph in which the height of each bar represents frequency or relative frequency. The difference is the bars are positioned in order of decreasing height. So you put the highest frequency first. You put the tallest bar first, and they go in descending order. Now this is good because it can kind of organize the data to show you what categories are the most important. So look at this example. In a recent year, the retail industry lost $34.5 billion in inventory shrinkage. Inventory shrinkage is the loss of inventory through breakage, pilferage, shoplifting, and so on. The main causes of inventory shrinkage are administrative error, employee theft, shoplifting, unknown reasons, and vendor fraud. But notice when you put them in a Pareto chart with the highest bars first, you can see that the biggest issue is employee theft, and a close second is shoplifting. So stealing is a big deal. It's a big problem for these industries. So it tells them what they should be focused on to try to improve the situation. Don't focus on administrative errors because that's a very small piece of the puzzle. Don't focus on vendor fraud. And don't focus on these unknown things. If you'll take care of the employee theft and shoplifting, that's going to knock out by far the biggest causes of the inventory shrinkage, and that Pareto chart helps us to see that. All right, next, graphing paired data sets. All right, paired data sets. A data set contains the cost of an item, and a second data set contains the sales amounts for the items at each cost. Because each cost corresponds to a sales amount, the data sets are paired. One way to graph paired data sets is to use a scatter plot. So you know all about this. It's using ordered pairs. Ordered pairs. So for the ordered pair that's described here would be, let's see, what did it say? The cost and the sales. So the cost will be the x coordinate, the sales will be the y coordinate. All right. Notice here this is called a scatter plot or a paired data set. The British statistician Ronald Fisher introduced a famous data set called Fisher's iris data set. This data set describes various physical characteristics such as petal length and petal width for 3 species of iris. In the scatter plot shown, the petal lengths form the first data set and the petal widths form the second data set. As the petal length increases, what tends to happen to the petal width? So you can see as the petal length increases, what is the trend? The width increases, because as the length is going up, the dots are going higher. So they're getting more width as well. So it's just these ordered pairs. All right, next we have what's called and this is the last one, a time series or a time series chart. All right, data set is composed of quantitative entries taken at regular intervals over a period of time. All right, so you could do like the amount of rain measured each day for a month. That's the measurement taken over time. So here's an example. The number of cell phone subscribers and the subscribers' local monthly bills for service for the years 2002 through 2012. So here's the year, here's the number of subscribers, and here's the average bill from 2002 through 2012. So all they graphed right here, they didn't even graph the average cost. They only graphed the number of subscribers. So the first order pair would be the year 2002 paired with the number 134.6 million. So notice the first data point is at that ordered pair, 2002 and 134.6. Notice they didn't put the millions, they just put in millions in parentheses right here. The next ordered pair is 2003, 148.1. And they put all those dots as those ordered pairs. Then they connected the dots to show the pattern over time. What is happening over time? It just basically shows that the number of cell phone subscribers is steadily increasing over time between the years 2002 and 2012. All right, that's it for section 2.2. Again, all we did was look at lots of different kinds of graphic displays of data. Good luck on 2.2 assignment. I'll see you again in 2.3.